For centuries, some math problems have been seen as just fundamentally unsolvable, kind of like locked doors with no key. And high-degree polynomial equations, they're some of the toughest locks out there. But what if, as this slide suggests, someone just found a new key? Let's dive in and see how a pretty revolutionary theorem claims to crack one of these ancient equations wide open.
So, meet our antagonist. This is an 18th degree polynomial. I mean, just look at this thing. It's an absolute beast with all these coefficients sprawling across the page. The challenge? Find the exact value of x that makes this entire monster of an equation equal 0. It's the kind of problem that's had mathematicians scratching their heads for generations. Honestly, it looks completely impenetrable.
Okay, so how would you even start to tackle this? Well, traditionally, you've got two main paths. On one side, you have the classical methods. They're powerful for sure, but they usually just give you approximations. Really good guesses, but still guesses. On the other side, we have a new contender, Azuti's theorem, and it promises something radical, an exact, perfect answer.
First, let's just take a moment to understand why this is such a tough nut to crack. It isn't just that it's complicated. For a very long time, equations like this were thought to be mathematically impossible to solve perfectly.
This is really where the old methods hit a wall. Techniques like Newton's method are brilliant, but at the end of the day, they're making educated guesses that just get closer and closer to the real answer. And that means you always have this risk of tiny rounding errors, and you can never be 100% sure you've landed on the exact value. In fact, Abel's impossibility theorem famously proved that there's no simple, one-size-fits-all formula for solving polynomials of degree 5 or higher.
But what if you could just bypass all of those limitations? What if you didn't have to guess at all? This is where our story takes a really interesting turn. Let's take a look at the new tool that claims to do exactly that.
At its heart, Azuti's theorem isn't about approximating. It's a system, a recipe. It's designed to break down a huge polynomial and then rebuild it in a way that actually reveals its exact roots. It's a direct challenge to that old idea that these equations are just unsolvable.
So how does this recipe actually work? The secret sauce is a concept called recursion. You can think of it like a detective solving a case. You find one clue, and that clue leads you directly to the next one, which leads to the next, until the whole mystery just unravels before your eyes.
Okay, here's the engine that drives the whole theorem. I know, it looks super intense, but you really don't need to be a mathematician to get the big idea here. This isn't a formula you need to memorize. Think of it more like a set of instructions. It's telling us how to use the information we already have from the polynomial to calculate the next piece of the puzzle.
So here's what that engine is actually doing. In each step, it methodically adjusts the terms of the polynomial, it uses some of the starting numbers, and, this is the most important part, it refers back to the values it just calculated. It's a step-by-step chain reaction where every calculation builds directly on the one that came before it.
Now, this is where things get really cool. After applying that recursive process over and over and over again, something completely unexpected happens. That daunting complexity we started with, it just begins to, well, it collapses.
See, the theorem's process generates a whole new set of coefficients, or building blocks for our polynomial. We'll just call them t's. There's one for each degree, from t0 all the way up to t17. The method just systematically turns through and calculates the exact value for every single one. But what it finds, that's the real secret.
This is the aha moment. This is the big reveal. After all that complex calculation, the theorem shows that most of these new coefficients are simply 0. They just vanish. It's an absolutely incredible, dramatic simplification that was hiding inside all that complexity.
I mean, just look at that. All of these coefficients, from S0 all the way to S7, they're 0. And then it does it again from S9 up to S16. They all perfectly cancel out. Out of 18 new coefficients, only 2 of them are actually left standing. Turns out, this polynomial was nowhere near as complicated as it looked on the outside.
And here you can see the effect. Our original monster equation, with all its different parts, it just shrinks. All the terms that were calculated to have a 0 coefficient simply disappear. All of that noise was just hiding a very simple signal underneath.
So what does this all mean for our quest? It means the problem we thought was impossible is now totally within our grasp. Let's look at the final, solvable equation and what it means. This is what we're left with. A beautifully clean equation with just 3 terms. You've got x to the 18th power, x to the 9th power, and a constant. Now this is something we can actually work with. It's the exact same problem, but we're looking at it through a new lens that shows us its true, much simpler form.
Okay, now we plug in the 2 non-zero coefficients that the theorem calculated for us. And yeah, they look like big, kind of scary numbers, and they've even got complex numbers in there. But, and this is the important part, they are exact values. There's no close enough here. These are the precise numbers we need to solve the puzzle.
And there you have it, the exact symbolic root of that so-called unsolvable equation. You know, its complexity isn't a flaw. It's actually proof of its precision. This isn't just a number you can punch into a calculator. It is the complete analytical answer. It's the key we were looking for all along.
The source material really says it all with this quote. The goal was never just to find a close enough answer. The goal was to find the real answer, no matter how complex it looked. And this method totally delivers on that promise. It gives us a level of certainty that just guessing and checking can never, ever offer.
And that really leaves us with a fascinating question, doesn't it? This was more than just a tricky math problem. It's a demonstration that a completely new way of looking at something can turn an impossible challenge into a solvable one. It really makes you wonder, what other locked doors in science and engineering are just sitting there waiting for someone to come along with the right key?